afternoon, gentlemen. I hope you all had a nice lunch. So if you're looking for a nice lullaby, here it comes. Sorry. So basically, I work for Toshiba Mitsubishi Electric Industrial Systems Corporation. It's a big word, but we just pronounce it as Tmeic. You will struggle with it initially, but it will come around. So the subject of today's discussion is basically what Mr. Manas wanted us to cover. Is return on investment with the inverter. So how the return on investment for solar projects are working. Hello? Yeah. So basically the subject that I need to cover is how the return on investment for solar projects could vary depending upon the reliability of the inverters. In order to ensure the reliability of a PV system or PV plant, what do we need from the inverters? So basically the main objective of our either a grid connected or a rooftop, any kind of solar plant, it is quite simple. To maximize the ROI and by generating the largest amount of energy at the least cost. So we have different components in the whole solar system, but then the key, most critical component is the inverter. So the objective of the inverter is basically to harvest the DC energy from the PV array and convert it to useful AC current, and also inject the harvested energy into the grid. So the most key, highest critical points for the inverter is its efficiency. It's the conversion efficiency. That means the lowest heat loss and auxiliary power consumption. And also the highest harvest efficiency, the ability to extract the maximum amount of energy from the PV array. And of course, CapEx, which should be the lowest capital cost, and then the reliability or the bankability and the regulatory compliance, etc. We need to observe all those. So what are the factors deciding the return on investment in the solar industry? Mainly from any component of the grid, of the solar plant. First is the technical, we'll split it into two. I can only talk about technical factors or financial factors, sorry. So if we talk about the technical factors, it starts from the beginning, the selection of the solar modules and the technology and the efficiency of the solar modules, whether it is to be crystalline or it is to be thin film. We know the problems in both the cases. In thin film it is a higher degradation, in crystalline it is the price. But then also when the second point is the selection of the PCU or the power conditioning unit, which could be either the micro inverter, string inverter or central inverters. So the basic, again, central inverters, their core job is to convert the DC to high quality AC, and they have to operate in extreme environment, and also the highest reliability is necessary. So the higher the efficiency, the better the yield, and the life expectancy must be within 20 to 25 years. And then finally the selection of the BOS, which is also very important. The lower the cost of the BOS, the higher the yield. And then we also have an efficiency across the entire system. So how do we define efficiency? It is by choosing very optimally the key components on each of the each component in the whole solar PV plant. So then we move on to another important aspect of technical factor, which is reliability. So the definition of reliability is here: the ability of an apparatus or machine or system to consistently perform its intended or required function or mission on demand without degradation or failure. This will ensure your ROI. So moving on to financial factors, the stakeholders. So the reliability of the entire solar plant affects the stakeholders as follows. For the investor, the effects, he needs desired returns under any circumstances. When you move to the developer, so the developer whose job is basically to integrate the stakeholders' requirements, and that is, he is accountable to the investors also. And then the integrator, who is EPC, and then he also plays a very important part in the whole project by ensuring or giving warranty for the whole project and performance. And utilities, of course, which is the RPO and the quality of power harmonics, etc., that they have to monitor. So nowadays, the competitive bids in the solar PV space, they are making it necessary for us to push the cost lower and lower, so that we can increase the yield and make the entire project financially viable. So moving on to the stakeholders' requirement from the inverter itself. Basically, the inverter can function, can perform its duty, and its key objectives, key features are, it has to meet the applicable grid codes and as per CRC regulations, etc. And then it also has to be very, very cost effective. And then it has its AC output is in existing prevalent conditions on the site, whether to do with temperature, dust, humidity, and maintenance also. And the quality of the output should be very clean, very smooth AC, and long lifespan, which is what we design our systems to be. And again, the auxiliary power consumption, it should have the least operational energy consumption, because that leads to lower OPEX, and then least operation and maintenance cost, that is as few spares as possible, and also the information and control of the system itself. All these factors contribute to a great extent the longevity of the system, performance of the system, and it ensures that the system itself is stable and reliable for a long time. So how do we categorize reliability? So we can talk about reliability in three main broader terms. One is the reliability of the software, let's say, where the inverter and all its different components have to function seamlessly, and it has to be time tested also and scalable as well. So, and then the reliability of hardware, highest quality standards in manufacturing process, incoming quality, and throughout the process, checking of quality, and at the exit and during the installation and commissioning as well. But most importantly, the reliability of processes which involves humans. This is where things can go wrong a little bit, unless they are monitored very, very closely. So I've talked about the quality processes at all stages, basically, which is 5S, what we follow in our production, and safety, of course, and installation. We have seen a lot of failures occur on the site due to incorrect installations. And execution and maintenance, again, over here also, these get taken for granted. And of course, this is where we see that the potential to mishandle and take things for granted is very high here. So how do you decide upon buying a reliable inverter? So of course, number one, when you go to buy anything as capital intensive as an inverter, you first ask around. And the first is its performance track record, in the local conditions of your site. If you can get a reference nearest to your site, nothing like it. But otherwise, it's important to find out whether the inverter can function, it is able to function satisfactorily within the same environmental conditions that we have prevalent on our site. So compliance to domestic and international standards. Again, these are standard, but then how important, how many times do we monitor and ensure that all these standards are followed? And each and every single project, you must make sure that we have these certifications for the single type of inverter. And then, of course, the availability of and factory test labs within the vicinity, or let's say within India itself, we have got ABB, ourselves, Schneider, Hitachi, quite a few guys are there, but then they have got local manufacturing facility. That gives you a lot of confidence to decide what inverter to go for. So, moving on to what are the reasons for failure of the inverter. So number one, basically it's the design part. We don't take sufficient margin or safety margins in the basic design of the components. I'll come to more details about the core component design in what Toshiba and Mitsubishi follow, but I'm just listing down. I've listed down only the core, the main items that we need to consider here. So selection of components. Each component, of course, must meet its extreme stringent quality, and then unavailability again of what we just discussed about a test lab and factory for quality assurance, and again inappropriate installation that's what we have just observed also. On the site, we have seen many times a perfectly designed system can fail because of poor earthing and not proper connection of the lighting arrestor, and insufficient air circulation within the room to dissipate the heat. And of course, poor operation and maintenance practices. And the most important, very critical aspect is the UPS system, which provides clean power to the auxiliary requirement of the inverter. And people take that also for granted. And although they spend a lot of time and money to design or to select the best inverter possible, but then when it comes to the UPS system, this one gets taken for granted, and then we have some failures over there. The UPS is the key component between the grid fluctuations and your inverter sensitive electronics. So we have this path curve for the PC or the inverter, and as you can see, the major, the first section of the path curve is it's the failure rate, which is called the infant failures. Again, this can be strictly avoided if we have got very stringent incoming quality measures put in place at the factory itself to check each and every component. So the main causes of failure here again is material defect. That's the reason. Then you go into the mid section, which is of the failure rate is quite significant also over there, which is again to do with the there are some failures which occur here due to faulty operation and either to do with the grid or to do with the operation of the inverter itself, and then wear and tear of components within the inverter, which happens. So it's supposed to happen during the last phase of its life after 20 years. So that's the component fatigue. So we have to ensure that on the first section, which is the infant mortality that is taking place, at that point, if you get things right, especially with very stringent quality measures in place, you don't have many problems going forward. The rest can be addressed anywhere which is not in your control, but then that can be overcome by very good service and after-sale service network throughout install base. So the index or ETCs for measuring reliability, we all know about these anyway. I'm not going to go into detail and definition of each and every aspect of these, but we track. We have so far installed more than about 2 gigawatts of inverters in India. each and every inverter, we have a track record of how many components we have replaced, what is the rate of replacement of each component, and where are the failure or weak points in the inverter itself. And that track record for each and every inverter, we have a unique database which is going to be monitored till the life expectancy of the entire solar plant. So, and of course, when you move to the essential standards, these are all, of course, to do with the hardware and the tests that we perform. I think everybody performs that because that is a must for to be able to have a long-term product in India. And then, so how do we improve the ROI in PV plants? So one is by minimizing the cost. Again, we discussed, I mean, you are all specialists here. I cannot explain much in detail about all these aspects. You're masters of this game here. So again, equipment and cable sizing has to be optimal, but at the same time, so sometimes we cut too much of the muscle and we go down to the bone, which is very difficult there. And of course, equipment selection. And of course, we also have a service, which is again supply and service for the OPEX. And we must ensure that you're talking to a company that is going to stick around for a long time within the solar industry. We see a lot of companies coming in and disappearing, and they leave a lot of their product on the ground without any spares and service, after-sales service. So as Tmeic, we have so far replaced about 78 megawatts of projects which have been supplied by inverters from other companies. Okay, so economies of scale again. The more product that you have on the ground, the lower your cost of production is going to be. And then, of course, we need to negotiate well with our vendors also in terms of delivery time and payment terms and also cost, the most important. And the replacement cost also for spare parts. So whenever we buy, I recommend to everybody, whenever you're buying an inverter, please buy a set of spares for the warranty period, which is nothing but it is just fuses, filters, and some SPDs. That's it. So how do you maximize? How do you improve your ROI? By maximizing the output. So the site selection, of course, is solar irradiance, whatever, that needs to be proper. And then the selection of technology of your PV module and your structure. A PV module, again, we discussed about crystalline or thin film. Structure, again, it can be single axis or dual axis, fixed tilt or tracker. And of course, the decentralization of MPPT to maximize your yield. This is again a critical factor. So, and the wider the MPPT range, the better the yield. And then the efficient design of the entire plant. How do you minimize losses? By designing the plant very efficiently, and on both full load and no load conditions. And the auxiliary consumption, we see that we lose a lot of revenue in the long term in auxiliary consumption. So this needs to be also looked into very carefully and ensure that it is the least, lowest or smallest footprint. And you minimize downtime as well. So this is basically the general approach to improving the ROI on the investment on the solar plant. I'll move on to the technology aspect, which is the conventional two-level design that was there before, which was being followed in this market. And in this design, the IGBT used to be stressed a lot, and the losses were much higher. And because of the stress, IGBT used to blow quite often. Within 3 years or 4 years, it used to go, and then it had to be replaced. Then in 2008, we changed to the neutral point switching, which is a 3-level circuit. And you can see that here the flow of the current is a little bit different. And here you see that by doing this, we are able to reduce the stress on each component. And by reducing the stress, you're able to get more life expectancy from the component itself. So, and then of course, the IGBT configuration that we use is also designed to ensure that the wider voltage range, therefore we have a much higher DC to AC ratio, and lower harmonic distortion. Therefore, it leads to a smaller filter reactor and a high efficiency at lower loads also. And losses are much reduced a lot because of the design itself. And you will see that it lives a lot longer. The component itself it survives a lot of shocks. Then again, we come to these are the comparative figures of 2-level, 3-level, and the new 3-level switching technology. And you can see that the switching losses and the conduction losses, both of them. So the switching losses are 74% originally in 2-level, down to 32% in the new 3-level. And then the conduction losses are a little bit higher because it switches so many times. But then overall, if you see, you've saved a lot across the entire component itself. So moving on to the MPPT range, again, this is a very wide MPPT range, and it is designed to ensure that you're able to extract even during cloud edge and also during the any peak. And also LVRT function is, or HVRT function is also much better when you have a much wider MPPT range. So again, you're maximizing the output from the inverter itself, and that's the best way to do that, because otherwise, this is the most cost-effective way, not the best way, most cost-effective way, by designing your software or firmware in such a way that you get the maximum MPPT window, through which the inverter will be able to produce power. There is a small comparative statement that our sales team uses regularly, but then I, for the sake of secrecy, I have just made comparator A, B, C, D, E. I'm sure there is up to Z also, but the key people in the thing. And this is what my sales team uses to fool the customers. But at the end of the day, this is what is very important as well. The 605 to 950 is a wide MPPT window, which ensures that you get very good return or yield from the system. And then, of course, it reduces the number of combiner boxes. And although it increases the modules in series, but then the heat dissipation is much lower. And then, of course, the generation over capacity, fault, write-through, and cloud edge, which is explained here also in detail. When the grid fault occurs, what happens, and then eventually your inverter rides through the fault if you have a much wider MPPT window. Then I move on to the MPPT's dynamic response to MPPT, which is the test that we had done in Fraunhofer Institute. And this was at 99.9%, but because it's a Japanese company, we will never mention that. We will just mention it is 98.6% or something, because the Japanese philosophy is that we will publish the worst data, because we don't want to publish anything that is the best scenario. The worst scenario has to be published. So that's one approach. So, and if I go back to the first installation that we did was in 1985 in a small 150 kilowatts installation in Alcoa, US. And the inverter was just running, and you can see the condition of the modules. It's completely degraded, and now it's just generating 60 kilowatts or so. But it was functioning. Nobody knew that there was an inverter also working over there until they went over there and found a fan fail. That's all. So just to tell you the basic philosophy, why the IGBTs, etc., last so long. The general industry takes the generic IGBT, which is available in the market. This IGBT is used for UPS applications. It's used in frequency converters. It is used in solar systems also, and other drives. It's a generic IGBT. But what Toshiba did was they designed a solar profile, load profile, IGBT for solar load profile. And the solar load profile is, you cannot use this IGBT in UPS systems or frequency converters or UAVs. It is purely for solar applications. And that load profile, they gave it to Mitsubishi Electric, which is the semiconductor manufacturer. And Mitsubishi Electric manufactures for us the IGBTs. And therefore, we have done maybe more than 350,000 IGBTs in the field now, and the failures are none, or maybe one or two, if at all. The reason is the junction temperature to which Mitsubishi Electric have designed their IGBT is 450 degrees centigrade. And due to the, I just talked about the 3-level switching. Because of the 3-level switching, the maximum temperature that you come across on the junction is 52 degrees centigrade. Therefore, the stress on the component itself is so low that you don't have any failures. And it's not a rocket science. It's just that they have packed in so much in that junction itself. Well, if you look at it, in the entire solar plant, the heart of the solar plant is the inverter. And the heart of the inverter is the IGBT. And the heart of the IGBT is that junction. At that junction, if you can take care of and ensure that the heat dissipation from our heat variance between the lowest temperature and the maximum temperature is as low as possible, then the component becomes smaller, the heat footprint becomes much smaller, and at the same time, the heat losses become much smaller. So then you'll see that our inverters are much smaller when compared to anybody else's. And that is the main reason for that. And because the inverters or the heat dissipation is much smaller, the fans, you'll find only maybe one fan, which is again rated for much lower RPM or much lower auxiliary consumption. So the weight and volume of the components and the heat dissipation and even the rooms are much smaller, just by addressing the absolute core of the IGBT itself. So moving on, the Tmeic experience, which I just talked about, was we are into the PV inverter technology since 1983. And of course, so far we have crossed 12 gigawatts of installed base only in central inverters, and a variety of experience throughout, from all across North America and a lot of South America as well, Japan, China very little, India 2 gigawatts, and Europe also not so much. But then there is a lot of experience throughout. So it is from that perspective, the most important thing is what we follow is the fact that for each and every system we have a thermal analysis, and we of course to validate the fluid dynamics, and also we optimize the specific local footprint of the site itself. And what we see what is going to be the impact of the inverter in that area, whether it is India or Rajasthan, or in India also we have done for Gujarat and for Rajasthan and for the south as well. And then we validate that technology, we run the heat run test and whatnot, and then we deploy the technology to the field. Because we just want to be just fit it, shut it, forget it way, because it's not possible to monitor, to send people on let's say 5 gigawatts of installed base and to ensure the uptime. The demand from the industry also is 99.5, 99.6 uptime. That means that either you have a lot of people on the ground, or you ensure that your product is extremely strong and durable. So we have this facility in Tumkur, where the Japanese Tmeic has spent about 500 crores to set up a 4 gigawatt facility, and it is 4 gigawatt per shift per year. And we work only 5 days a week, only for 8 hours. But then during the time from January to March, we work for 28 hours every day. It's like that, so it's too much. So that then it peaks over there. So it's very difficult. And then, okay, that's the footprint of what we have currently as of FY 2016, which is 31st of March, where we could open a champagne bottle because we crossed 2 gigawatt in 2.5 years. That's it. So that's it from me. Thank you very much for your attention. Did I? It's only half an hour.
Any question?
I have a question. You were mentioning the bathtub curve on the reliability.
Yeah.
The first part of the phase.
Yeah. Infant failures.
That's right. You talk about in hours or days or weeks or what?
This is the definition which is across the industry. It doesn't, I mean, for the PV inverter, you would talk about the in hours, uptime hours. And uptime hours would mean that from sun up to sundown. Okay, and that depending upon the PV system, whatever we can calculate. So your definition may vary from my definition because there is no, in the solar industry, we don't have a firm definition yet.
Thank you. I want to know about product range, from string inverters to central. Full range you have? You manufacture?
No, we have only the central inverters. We don't manufacture string inverters. So our smallest inverter starts from 500 kilowatts, and then 750 kilowatts, 1 megawatt, 1.8 megawatt, 2.7 megawatt, and 3.2 megawatt. Single block. We don't have anything string. No.
Looking at your reliability of equipment or inverters, you have any plans to get into the smaller segments? Because the volumes are really high.
No. The volumes may be very high, but I think many people will tell you here that there is no juice.
Yeah, of course.
So it's difficult to run a business with little juice. The margin is so thin that you sneeze and it disappears. That's very difficult.
But there's a, even any other manufacturers, they have their own network or dealers, channel partners. But can have a similar, because of how do you have a name and fame plus reliability and a design?
Yeah, again, you're looking at a 20 to 25 years marriage here.
Yeah.
It's going to be, and personally, I'm not fully convinced of electronics itself, in the sense that if the entire product itself is just mostly electronics, I don't believe that it's going to last 20 to 25 years. I would rather have a huge inverter, central inverter, where we have small electronics, which we'll replace. It will cost a little bit. But for the string, entire inverter has to be replaced. So anyway, there are two sides of the same coin. Many people believe that the string is very good, etc., etc. But then many people believe the central is okay. So, but you need to follow your philosophy, which is your company's direction. And we decided to go with the central.
Thank you.
Normally, what is the design life of the inverter you consider, and what is your warranty terms? Like, do you provide warranty for the complete 25 years? Or?
So the first part of the question, we designed the product for 25 years, and the standard warranty according to MNR is 5 years. But then there are some projects where we have signed up to 25 or 20 years, I think, with some people, 20 years extended life warranty. But then we have a separate cost for 6th to 10th year, 11th to 15th year, and 16th to 28th year. We have different costs. And then we replace the components irrespective, whether they fail or if they don't fail, we will replace them. Like there are certain capacitors, there are certain components like capacitors, 12 years we have to replace them. Fans, 6 years or 5 years we have to replace them, whether they fail or not.
So in simple terms, if the extended warranty option is considered, then we need not replace the inverter after 12-15 years, because as a developer, some people do take the model that maybe after 12-15 years it needs to be replaced once during the lifetime.
No, you don't have to. That is not required at all. See, Toshiba and Mitsubishi, again, we come from the oil and gas background also. The oil and gas in offshore platforms, you have got 20 to 25 years life expectancy. You can't just go and change in an offshore platform where you need to take a helicopter or a barge to replace a small fuse. It will cost you $14,000 to just go and come back, only to replace a small fuse. It's kind of, so the design has to be so solid, and life expectancy has to be so good, that so long that you don't have to replace the components.
Okay, I got another question. See, typically, like all inverters do derate with temperature. Of course, each inverter has got a different rating at 50 degrees centigrade and higher rating at 25 degrees centigrade. My question is cabinet temperature typically, especially for the indoor inverter, is always higher than the ambient temperature, irrespective of whatever heat removal system you have in terms of providing the exhaust fans or whatever things are there. So, can you throw some light, when you calculate the degradation, is it the ambient you consider, or is it the cabinet temperature is to be considered while calculating the derating of an inverter?
Basically, you need the inverter by itself. Whether you keep it inside a room or you keep it inside a container, it's up to you. When we do the testing on the most hottest part of the inverter, which is the IGBT. So at the IGBT level, we have got 95 degrees. We need to go down to up to 95 degrees. But then at the ambient, which is about, I think from the IGBT we have about 1 foot or 1.5 foot away, we need to have 50 degrees. So thereafter the derating starts, 50 to 55. And 55, it's cut. So the derating is only after 50 degrees.
No, I'll just put my question a little differently. When you do the PVC simulation, and suppose I am evaluating the performance of an existing plant, and I replace with respect to the actual weather conditions. Now, typically what happens that there is a established fact that, okay, what is the ambient temperature and how that gets converted into the module temperature, because module degradation is one of this thing. And also there are module sensors or like temperature sensors also there. You can validate with that yes, ambient to module temperature, what is the correlation. When I come to the inverter, typically with the inverter I get two temperatures in my SCADA. One is the cabinet temperature, second thing is the IGBT temperature also. Yeah. But the simulation still takes the ambient temperature. So
that's in the PVC, is it?
Yeah, it is in the PVC. So that's what I'm wondering that, and that ambient to cabinet temperature is a function of the ventilation system provided by a EPC provider for that particular thing. Suppose that room is not very efficiently designed, there can be residual heat.
So where is this transducer located? Is it inside the cabinet of the
inverter? It is inside the cabinet.
Then it is an inverter component. For example, anything that is inside Tmeic door is a Tmeic component. Therefore, that gives a reference point that to the firmware software for us to control the load and to ensure that the inverter goes down to in its output. So you need to refer to that one, not the ambient one outside. The ambient one could be very far away from the main heat generating point. This data is very crucial. So if you take the wrong reference, you will have wrong results.
Okay, just my last question. Sorry for too many questions. Do you demonstrate the inverter efficiencies at site also?
Yeah. Inverter efficiency, we can demonstrate that, but it is straightforward anyway, because you just measure the input and measure the output and use the efficiency straight. And you are measuring right at the inverter input to the inverter output. Okay, that's what we confirm that our efficiency is between these two points. Yeah. So from that point to this point. So whether those 2 points are existing in the factory or whether they are existing on the site, it is the same points. So we can repeat that test also on the site. It's not a big deal. No problem.
Thank you.
Thank you.
This is isolated inverter or not isolated?
Isolated in the sense?
Output is isolated?
With the transformer, you mean?
Yeah.
So no, we have got the 3 phases feeding into a transformer. The transformer is not a part of our scope. So whether you want to float it or whether you want to ground the neutral, it's up to you.
This is pure sine wave?
Yeah, pure sine wave. Absolutely pure sine wave. Sorry.
One of the slides you mentioned you have a higher AC to DC ratio.
Yeah.
Can I know what are the AC/DC ratios that you have in the different makes and models?
Officially, it is 26%. There are some companies here whom you know well, but we have gone up to 40%, and it is working for 2 years now because they decided to push the inverter further. And it's actually unlimited. It clips automatically. So no matter how much DC you overload, the inverter clips automatically. So the clipping takes place well over 1.46. But we will publish only 1.26. And we have, in exceptional cases, we have given confirmation to go to 1.4 also. Not more. So, but then that again, it's due to this wide.
So what is the maximum correction factor that we can achieve using A50 or
Maximum correction factor?
Yeah, maximum correction factor what we can achieve using general Fourier series or A50.
Wow. Man. That is a deep one. I don't know.
So what factor we can achieve? The maximum factor we can achieve. So for the conversion from DC to AC.
A maximum factor?
Yeah.
We can achieve, huh?
Yeah.
Okay. 1.46 you can go to. 1.46.
It is 3 cycle or it can be increased to 6 cycle also.
Yeah, not in many, but.
So I'm very new to this one. So
Me too. This part is on new.
so this is
जो मैं पढ़ के आया वही सब्जेक्ट में से क्वेश्चन पूछा मेरे को मैं आंसर दे दूंगा no I really don't know to what extent we can but I know that we have been using to 1.46% factor, but then it's again not allowed by MNRE, I think even the grid operator also, to go beyond a certain 1.1 or 1.15.
thank you.
Sir, you were mentioning about the IGBT's efficiency.
If you ask me a difficult question, I'm not going to give you the order.
No, this is not a difficult question. I was just, wondering if Tmeic has taken steps to move towards silicon carbide-based MOSFETs instead of IGBT for better efficiency and lower thermal coefficients. That's it.
You mean the SI?
SIC.
Yeah, we are.
Okay.
Yeah, so already the system, the next 7th generation IGBT is coming SI.
Thank you. Sure.
Luckily, I remember that.
Thank you, sir. Thank you.
So we are into frequency converters also. So we have the new 6th generation is already out now. 7th one is coming with CSI, with SI. Sorry. Yeah.
So I think, can I answer that 3 to 6 cycle?
Yeah. Yes, thank you very much.
Out of course.
Thank you very much.
But what you probably need is how quickly you ramp it down.
yeah.
Right. So it depends on what programming you do. Are you into LVRT mode? Are you in a shutdown mode? Which mode? So these are all programmables, and this is typical of the grid requirements. So your question will depend on what mode the inverter is in. So that brings to another out of course question to you. But it's not through the technology, but LVRT and reactive power export. I guess you do both of them.
Yeah.
What are the regulations right now in the country, state-wise? If you know, different states have their own bills and fences about this. Some people know what it is, some people don't know, so you educate them.
Yeah.
Where, for example, Karnataka is still debating, I guess, both LVRT and put capacitor bank or live with reactive power. So where do you think the industry is likely to settle, or the utilities will settle with most of the inverter fellows?
See, whatever is the most economically viable solution will
Well,
work.
LVRT doesn't cost you money,
So, yeah, but then
but it's a requirement.
yes, it's a must now. So again, I feel that the capacitors is the best solution for. I mean, you have to see what solution will lose you the least amount of power. Okay, So the capacitor bank seems to be doing that very purpose.
I'm referring to capacitors out of the inverters.
But
Now,
that is
the question-
LVRT function.
The
Yeah.
question is, no, this is secondary question. The question is, people have been complaining of power factor being an issue, where you are already producing at unity power factor.
Yeah.
Right? The question is only in the night time when the main transformer is still up and running, you have a lot of reactive power in board.
Yeah.
And that is where could you switch your inverter to an exporting method?
Yes.
Because Karnataka has been fighting
Yeah.
with developers on that issue.
Yeah.
I think we need to
So,
explain that.
so we have got a nighttime reactive power
That is it.
generation
Right.
and daytime
And
reactive power
post-
compensation. Yeah. So that's where the design and the new CE regulations also ask for the same thing. That has been. I'm glad that they do, because that has been a standard feature of the system since quite a long time. Although it was not very much mandatory in India, but in the US and everywhere else it was necessary. So the firmware is exactly the same thing, what we have, which we are using in our components, inverters elsewhere. So it already addresses that. So, but then again, I think the most cost-effective solution will go forward, which is to do with the capacitors only. Nighttime reactive power generation. So we have a software which sits on the substation side and which sits on the inverter also. But then they need to communicate. So the medium, I mean, either through the substation or to the grid, we need to provide that. Or you have to lay a separate cable for that, or separate wireless communication. Because sitting there, that device will instruct the inverter to now switch to generating reactive power. Or to what extent? So we have got 3 or 4 levels where it go down to 70%, 30%, 50%, 30%, and 10%. So depending upon whatever the signal comes from the device sitting on the substation side.
Are all inverters having reactive export management available in India?
Our inverters
No, most of your.
should be. Our friends and colleagues, yeah.
Yeah.
It should be, because I think you are looking at an investment for 20 to 25 years. You need to factor these basic things
No,
for sure.
I'll tell you why, because Bascom has been insisting on capacitors.
Yeah.
And I said capacitors have a lot of switching issues.
Yeah.
Damage the inverters and the system.
Uh-huh.
And then you have a fixed reactive power. So unlike you, where you can actually control it. I'm pushing the reactive power with the local guys.
Yeah.
I wanted to hear from you.
So we are open, because in different countries it's different. And again, depending upon, even within states also it will be different. Even between BESCOMs also different, it will be different. So we can't have a special inverter design for Karnataka and one design for Gujarat and one design for MP.
Quick question.
This is your last one, your quota is over.
Yeah, this is just the second one, but I'm sure it's the last one. Why isn't your factory solarized yet?
Good question. Okay, so we are in the process of. There is one gentleman sitting in this room who is doing the rooftop for our system, for our factory. And
Could have been
okay. Sorry, too late. Maybe the next factory.
possible.
So no, we are doing it's a 750 kilowatt plus we are buying open access power also. So our inverter is also becoming green now, because they are using green power to produce green systems. So it will be a totally green inverter. So the factory that you see there, the last one, yeah, all that rooftop is entirely green. Plus, we are putting, Toshiba and Mitsubishi, they invest heavily in the storage system also. So, we have a battery, ESS, energy storage system as well. Plus, we are buying open access. So, it will be the entire factory is going to be powered up by pure green power.
So you have one slide. I think I don't need mic. Okay. You have one slide where you compared the MPPT ranges with different competitors. Have you done any performance evaluation of inverters which start at lower voltages? Because the many inverters start at low voltages. And like, what is performance like if you compare it over a time? Like, is it better to have an MPPT starting from lower range or a higher range? How is the comparison standing in terms of
The important thing is the bandwidth.
how
But how wide the
like
bandwidth.
on the higher bandwidth, like if you see the climatic conditions, like what is the proportion of time you will have an inverter functioning at the highest level of the voltage levels compared to the lowest voltage levels?
So basically, that's the point at which the module starts to degrade very low, or that's a degrade when the module is degraded. But mostly, if you see, this is where the MPPT should be. So when you talk about you're talking about inverter waking up voltage or inverter MPPT voltage.
MPPT voltage.
MPPT voltage that's a sweet spot. So if you have a lower one, you will be only you can put only.
You still generate something.
Yeah, you can put only a certain limited number of modules in series. But then when you go on the other side, suppose, okay, this is the time when it is going to start, right? What about the maximum side? So where is your compromise going to be? Should you go on the lower side or should you go on the higher side?
Higher side, if you see at the very high side, you really don't generate anything because that's a condition which comes very rarely.
Yeah, but then every time you go into that spot, you lose a lot of power. Cloud edge or any kind of rate fluctuation, LVRT, you lose a lot of power.
But that's something like between the inverters. Has anybody done this comparison, like which is like performance? If you consider these areas, like everybody compares the inverters with the sweet spot. Like,
Yeah.
I would say like in sweet spot, almost all inverters will probably perform to the best levels.
Yeah.
What is it happening in the two varied zones, and what is the performance during these areas will actually make an inverter differentiate with other inverters?
At the end of the day, the yield from the inverter, that matters. No matter how you do it, whether you do it this way or that way. But then you need to factor in long-term impact on the module degradation also on the inverter itself. Because inverter is not by itself a standalone.
Yeah, because see, many people are actually compromising on the lower side. They're going till 450 also in the MPPT range.
Yeah, but then you look at the top also. And then again, it's simple electronics, electrical. The more voltage you have got, the lower current you have. And therefore, the lower losses you have. And therefore, the efficiency is much higher. So if you stick to the higher, otherwise people would have just been putting only one module in parallel. And everything would be.
But when you have this higher, this one, your waking voltage is
No, I'm not talking
how
about
is your
that's
waking
what I was
voltage
talking
compared to
about.
other competitors?
Everybody wakes up similarly at
The
the
same
same time. Yeah. But then it's again when you generate the maximum.
Okay.
That's important.
Any further questions? Mr. Abbas? No, I guess that will be all, sir. Have a nice
Thank you.
presentation.
Thank you very much.
Thank you.